phrase I like to think of is every time you see a hinge, take a moment. Meaning that whenever there's a hinge, I'm going to want to cut it at that hinge. And since hinges do not pass on any moment internally, I can take a moment at the hinge, and it gets me an extra equation to be able to solve my problem. Anyway, let's see what that actually looks like. So I have just a regular cantilever beam with a hinge in the middle. I have an extra support at the end, however, which means that I need this hinge in order to solve it. Otherwise it would be statically indeterminate, and that's a whole different story. I have a distributed load as well. So the first thing I want to do in order to draw my shear moment diagram is I want to solve for my reaction supports. In order to do that, I'm going to first draw my free body diagram for everything together, as if there was no hinge. I'll still draw a little dot just to remind me, but I'm not going to consider any internal forces there. So this is my moment at A, coming from my fixed support. This is my vertical reaction at A, and this is my vertical reaction at C. Just to remind you, on beam problems we don't consider any axial forces. So that's why I don't have anything on either side for our horizontal reaction. Let's see what I can get from this situation. If I take a moment at A, some of the forces at A, I have to include my moment at A, which is negative, and I have a positive moment from CY. Oh, I forgot my distributed load. That's actually a common mistake, and your TA made it, so watch out for that. Okay, negative MA, CY, 10 feet, and then here I have my distributed load times the distance it's applied, and then it's acting as though it's right here in the middle, so my moment arm is 5 feet. That means that my moment should be CY times 10 feet. That was a negative moment. Minus 2 times 10 times 5 is 100. My units have kip per feet, and feet, so it's kip feet, which is the units of a moment. Force times the distance. Alright, we can't really get anything more from the moments. I could go from the other side and get m in terms of AY, but I'm not going to get any solid numbers. Let's see what we can get from looking in the vertical direction, summing the forces. I have AY plus CY minus my distributed load times the distance it's applied. And, well, this really doesn't tell us much either. I have two equations that I've used, and that's all I have before I use the hinge. And so I wouldn't be able to determine anything if the hinge was not there. That's why I would call it indeterminate without the hinge. So what do I mean with having the hinge gives us an extra equation? That means if I cut right there and I look at each half, I will be able to solve this equation. It'll give me a third equation to work with. So let me draw what that would look like. The left side alone, I'm going to have some kind of shear force. Oops. Positive member notation, that's important. I'll call that VB, and I'll keep the rest the same. AY and MA. It's important that I draw these the same directions. Once I've labeled it that way, that I keep it that way for reaction supports. Internal moments and internal shear are a little bit different. That's because for every action there's an equal and opposite reaction. This is the other side to that same force. When we put it back together, if we were to stick this one on the end of that one, we would be able to add those two up and it would equal to 0, which is what we have here. Essentially that's a principle of superposition. CY is still up because it's a reaction support. And I do not have any moment reactions internally because it's a hinge. If I were to cut anywhere else, I would have a moment. So, where's this extra equation? I can get it from the left or from the right. And again, I almost forgot my distributed load. 2 kip per foot. This is acting based on the middle of each segment. Let's call this member AB and this member BC. Member BC doesn't have a moment, so this side would be easier. That's the one I'll start with. Sum the moments at B, because I don't know VB yet and I want to find CY. So I'll sum the moments at B. Okay, I have my distributed load, negative direction, 2 kip per foot. It's applied to 5 feet of it, and the moment arm is 2.5 feet. CY is in the positive direction, and its moment arm is 5 feet, equals 0. 2 times 5 times, well, 5 divided by 2 would give me 25 kip feet. And then, so that's negative 25 kip feet equals negative CY over 5 feet. So CY equals 5 kips. See how this extra equation gave us one of the values of the reaction supports. Now I can go through, I could plug CY into this equation and get AY. I could put CY into this equation and get my MA. So that hinge gave me an extra equation. Let's continue trying to solve the rest of the reaction supports using the right and left side, however. And then we can check our answers with our original equations. So let me try to find VB so I could know VB on this side. So I have CY equals 5 kips. Let me take the sum of the forces in the y direction so I could find VB, and then I'll know what VB is here. So VB plus CY minus 2 kip per feet applied across 5 feet equals 0. VB equals 2 kip feet times 5 feet minus my value of CY is 5K. That equals 2 kip per feet times 5 feet is 10 kips minus 5 kips, so VB equals 5 kips. Positive member notation is that way for a reason. It's equal and opposite, meaning that this 5K is 5K here and 5K on this side. It's a positive value, the direction that I've drawn it in both cases. That's why we have a positive member notation. So let's look at our member AB now. Since I know VB but I don't know AY, I'm gonna take the moment at A so that I can find what MA is. Sum of the moments at A, I have negative MA, and I have a negative VB times 5 feet. Negative 2 kip per feet times 5 feet times 2.5 feet. Okay, so let's take the moment at A on our left side so that we can solve for MA, now that we know VB. So I have my negative MA minus my VB times its moment arm minus my distributed load times the distance it's being distributed times its moment arm. And that gives me MA equals negative 5K 5 feet minus, and this gives us 2 times 5 times 2.5 is 25. Kip per feet times feet is kip feet. So this should give us MA equals negative 25 minus 25 is negative 50 kip feet. Now let's see how that would compare if I were to put my CY into my first equation. CY would be 5K. 5K times have 20 F feet. That shouldn't be that way. So 5 times 10 is 50 kip feet minus 100 kip feet gives me negative 50 kip feet, which is exactly what I got here. I could really be confident with that answer. Okay, let's do sum of the forces in the y direction for my left side. I have AY minus 2 kip feet VB equals 0. AY equals 2 kip feet times 5 feet minus 5 kips equals 0, which equals 2 times 5 is 10. Oop, that should be a plus. 2 kips plus 5 kips. AY equals 15 kips. And let's see what would happen if I had to put CY into my second equation up here at the top. I have AY plus 5 kips minus 20 kips. If I put that on the other side, I would have gone AY equals 15 kips, which is exactly what I got. So that would be my answer. This gives us the reaction supports, and we were looking for drawing the shear moment diagram. So we got our reaction supports, and I need to draw my shear diagram now. So I know my max value is going to be 15K. I'll say this is 5, 10, 15, negative 5, negative 10, negative 15. And at the very end I'm going to have to go up 5 again. So I can do a straight line straight between these two. Now why doesn't this cross at the hinge? That's because hinges don't affect shear, they affect the moment. Hinges still transfer shear right across. So the hinge is right here, but you can't really tell until you look at the moment diagram. So let's look at that. Okay, where do we start? We're starting at negative 50, so I should have that too. Let's say this is negative 50 kip feet. This is positive 50 kip feet. So we start down here, and we're going to be gradually adding area until we get to some peak here. And I have no moment here at the end. And I know that it's going to peak right where the shear is 0. And as I thought it would, the hinge ends up being right where the moment is 0. And this is always going to be the case. On my moment diagram, wherever the moment crosses at 0, that's where my hinge was, if I have a hinge in that problem. Alright, and that concludes that problem.